fact, I am dialing in today from there for you. So yeah, I'm pretty far from Uganda. I do hope that I could join you there. It would be amazing, but it wasn't meant to be this year. Maybe in a future PyCon Uganda. So I became a core dev in 2010. That was a long time ago for me right now. My life looked very different from where it is today. I also lived in Poland at the time, and now I'm back here. But in 2013, I got hired by Facebook, and while being there, I met with other core developers face to face. That wasn't really something I could do when I was sort of remote in Poland. There was no other core developers in Poland. So in California, I met Guido van Rossum, and we worked on bringing typing to Python 3.5 with PEP 484 and so on. So that's something that the actual location for me in California definitely helped with. So I also realized this, that meeting people in person was important, that this actually allowed a lot of information to flow that otherwise would just not happen. The thing is this, there is a lot of things that you can learn over this course. There's a lot of things that you can learn otherwise online. And now with the post-pandemic remote working environment, with me zooming into like your conference, you can clearly see how we can in fact work remotely. But I still felt like there is something magical about human to human interaction in real life. In 2016 and 2017, I organized core sprints for Python 3.6 and 3.7 later at Facebook at the time to bring some core developers together. And this actually caused a lot of, I don't know, like activity that otherwise I'm pretty sure would not happen. In particular, at the time, Python 3.7 core sprint week was the most active week in Python's history. Like now, like we're a much bigger team and we're working much faster thanks to GitHub. So definitely we're in a different sort of time right now. But this kickstarted some of those developments that we have. And over time, I also authored some of my PEPs. So, adding a single function to functools, single dispatch, one package retention policies for PyPI, the annotations future import that is now being replaced by YLZ PEP 585 that actually made annotations built-in collections actually able to use generics in function annotations, and so on. Well, like the thing that I'm probably most sort of known from today is that I am the CPython developer in residence for the Python Social Foundation. So I am a person being hired by the PSF to work full-time on things attached. So that's the best job ever. What that entails is mostly doing core reviews and making sure that the bots and other automation we're using stay in, it's dependable, and people can be non-blocked by this backport. So not really my own pull requests, but making sure that the fixes that we make ready actually can come back to previous versions of Python. So currently, if you make a bug fix in Python, you're going to make it in the main branch, which is going to be Python 3.14 in the future. So when we're doing that, that's not going to fix Python 3.11, for example. So you have to backport to 3.13, to 3.12, and then to 3.11. Sometimes this is very clean and automatic, and there's bots that help us with this. But every now and again, there's going to be a complication because the code, I am the person hired by the PSF to help with those things. So yeah, I like this a lot. It allows me to actually be productive from Poland. I don't really have my own. Well, there's one now in Python 3.13. We're going to talk about it a little today. But I'm also the release manager of Python 3.8 and 3.9. So I want to talk about this for a while. So what does a release manager do? Well, they cut releases. What that means is when we have enough of Python ready, we are tagging it as a particular version of Python and release it. Obviously, releases that a release manager does is the 0.0 versions, right? So for me, it was Python 3.8.0 and 3.9.0. But those are just two of very many releases that you're making. Like first, you're making Alpha 1, Alpha 2, up to Alpha 7. Then there's betas, and then there's release candidates. And after the 0.0 release, there's bug fixes that you're doing. 0.1, in case of Python 3.8, we all the way to Python 3.8.20 before it went end of life just earlier this week. So when we're cutting releases, it is very important for our users to know when this is going to happen and how big of a change it's going to be compared to the previous version. So this process has been pretty, how would you say, ad hoc. Every release for Python 3.9 released Python when the release them every 18 months. Reality, 24 months, you couldn't really depend on this and not depend on the time of the year when this happened. So I saw this as and for Python 3.9, I decided to releases dependable and make the releases timely. So I proposed 602, the annual release cycle for, and this essentially made Python kind of tied to the calendar year, where we know for sure that there's coming after the previous version of Python is released, and betas in May, and release candidates in July, and final release in this just happened right now where we have Python 13 already. Release man Thomas in fact should say is, because he's gonna be releasing Python for you for the next 5 years. It's a long process to actually be able to say this version of Python is end of life, meaning no new releases are gonna appear. 3.8 only reached this status, so 3.9 is still yeah, so pretty large sort of set of versions that we still support. So this PEP was accepted, which is why we have this process right now, which is very helpful for many reasons. For example, Red Hat with Fedora is including the current version of Python that is currently developed on their next Fedora version that they are also developing at the same time, which means when the newest version of Fedora comes out, it already comes out with the newest Python possible, with the newest Python that there is. That was only possible because of the kind of interlocking of our schedules. And that was a deliberate, explicit goal of this PEP. So that's great. It not only gives Python faster to the users with the newest version, but also allows us to find many problems with the Python version that now, such that Fedora finds them by testing Python with their own packages and with third-party packages that are also packaged by Fedora. So I personally think this is great, and very many people are using the fact that this is a dependable feature of right now. But there are people concerned about this, say, but if you are releasing Python every year now, isn't it too quick? Isn't it making moving between Python versions more complicated because there's more backwards compatibility breaking changes, and there are just more features, more changes. So a regular developer now needs to put more work into staying current. So my answer to this is that not really. The reason why is the same core team. And we still are only able to push out that much code in terms of features and fix that many bugs and deprecate as many APIs that need to be removed in the future and so on. So this is the same salami, only sliced thinner. That's why this picture is and that was always my argument, that we're not really accelerating anything by the annual release cycle. Did the amount of changes in Python accelerate in the past few versions? Yes, but that's because the sponsor development is not precedented. Not only do core developers and residents like myself and Peter and Sierki are getting paid to do this work, but there are multiple teams at different companies that actually specialize in Python core development. We know that there is a rather large group of people at Microsoft working on making performance better. Meta has a big team that not only maintains their fork of CPython called Cinder for Instagram, but also the removal of the global interpreter lock. We're going to be talking about this as well, and so on. So Bloomberg has people who are hired to work on Python, if not full-time, then a better chunk of their time, and so on and so on. So that we see not because of the annual release cycles, but because of the better investment, as of the growth in the team size, it is clear that there's going to have the large that are fundamental, like the ones that you're interested in hearing today. So what you need to, those changes are impossible to be introduced within the scope of 12 months. It's just not going to happen. There's too much things that you need to write. And what you need to understand is it's not even 12 months. The actual working on introducing new between October and May. So between those two dates where there's alpha versions of the new version of Python. So now Python 3.14 is going to end, well, it's already sort of in alpha 0 stage. Hugo van Kemenade, the release manager of Python 3.14, is going to release alpha 1 early next week. So that's going to be alpha 1 out of 7. And that is the time to actually develop new features. In beta, we no longer develop new features. At this point, we're going to be only focusing on fixing problems that with the features that were already added to the currently developed Python version. And there's going to be a new branch for the next version. And Python 3.14 is going to be sort of frozen in terms of bug fixes until 0.0, after which we only do security releases for 3 years. And hence, I said Thomas Wouters now is going to have 5 years of release management. So let's get back to the longer than one release to develop. This isn't really only a feature of this new annual release cycle that this is happening. This has been happening all along. In fact, even in the late 1990s, we already had like this meme that Guido has a time machine. The reason we said this was people were often finding that they can already do what they wanted on a mailing list to ask about, do something because of some obscure thing that Guido did in the past. So the joke when somebody went to ask, like, hey, like, it would be awesome thing that I could do to his time machine 5 years to implement it very quickly, and then came back for 5 years. So that was the joke. That's how early internet memes looked like before images and now videos and so on and so on. And this was true for many reasons about how doc strings are readable at runtime, about how flexible the sum built-in is, and so on and so on. And in particular, even in early 2000s, like here in 2001, Tim Peters, the author of ZenPython, ZenoPython, that he wrote 3 years later after this email, he wrote here that I see Guido used his time machine to ensure that his style guide has never recommended mixing tabs and spaces. So see, even 23 years ago, we already had conversations about tabs and spaces and formatting and forever, stuff like that. So somebody should write a tool like that automates all this. So that would be a great idea. So in any case, took a while to take shape. Like function annotations were added in Python 3.0, but they only became type annotations in Python 3.5. So for 5 whole releases, it wasn't really clear what they're going to be used for. And coroutines that you have in Python right now, and you can depend on them as part of async and await, async IO, and so on and so on, they actually were made over many, many releases. They were added over Python by making generators smarter over time. So this sort of evolution of the language over many releases was always the case. Talk to you about some of the releases that we're going to have in Python 3. But before we get to that, let's get a little practical so that this keynote is not generated images and me talking to you like, about, oh, things were so different back in the day. I love keynotes, but I also love like a technical talk where you can learn something that you can use later on. So let's do a little bit of that and talk about what makes Python an interpreter. So let's interpret this expression together. What is this operation? If you use a single word, say, what is this doing? The high-level operation here, which might not be very easily seen at first, is that this is a sum. In fact, it's a sum of two things, of a product and of a division. It is more obvious to see this if you actually change this notation, this mathematical function calls. So for example, we can say that the outer function that we have, and then inside you have two arguments. The first is this product, which is this multiplication of A and B. Argument is this division. Another multiplication inside of C and D, and then the division is by E, right? So that already a better idea of what the order of operations is going to be, but still you need to know how to read what those arguments are doing and how they're going to be evaluated to actually say, what is Python actually going to do first? We don't know yet from just looking at this. So let's figure this out and actually try to evaluate this entire operation right now. So first, we're going to be evaluating this A times B, which is easy. We can, calculate it into a number. Let's call this a triangle. It's the yellow triangle. That is the result of the multiplication. There's nothing extra we need to do here. But the division itself needs a subcalculation. So let's go for that first. So first we need to do this multiplication of C times D, which already has a result. And we just move E upwards. And after that, we can finally do this, giving us this, matter or whatever that is. And finally, we have two already values, so we can combine them together and result of this entire complicated expression. So if this looks like a tree to you, good, because that's how Python parses your code, and it changes the source code text into a tree that it then knows what the order of operations is going to be. So it knows what bytecode to generate for it. But wait, what is bytecode? Let's talk about this now. So if you write this function in Python, which takes 3 arguments, E and E, and have the same expression that we talked about inside that function, we can actually ask the interpreter, like, what are you going to do with this? What are the bytecodes here? What is going to be the order of operations? And the order might be a little surprising to you. And the reason Python is an interpreter language, and it's a stack-based interpreter. And we're going to be talking about the stack right now. So to see what the code for a given function is going to be, you can use the dis module from the standard library. You can import the dis, call it with the function that we want to decompile, that we want to see what byte. And if we do this, you're going to a bunch of things that you might have seen in the past when you're a Python developer, but maybe not. So let's explain them right now in maybe kind of sufficient detail that you know what is going on. So as I said, Python is a stack-based interpreter. What that means is at any given point, the current bytecode, it will take the data that it needs to complete the calculation from a stack of values that it uses. So at the start, the stack is empty. There's nothing happening just yet. And then we have to load the values that we want to actually execute this A times B operation. So we load it fast. This is a local in our scope. A local because it is an argument to our function. So we can load it fast. We load A, parentheses on the right, load A, load fast A. Global B, it's global because there is no local variable called B and there is no argument to the function, which means it lives in some outer scope. Maybe we imported it, maybe it's a global variable. So we load global B. And then we can call a binary operation with the argument being star asterisk, so multiplication. And that binary operation needs to from the stack. How many values does it need? 2, because it's a binary operation. So it's going to fetch 2 from the stack. Well, it fetches B, it fetches. Now the stack is empty again. Well, everything that we loaded by this binary operation. And then it's got a result. Where is it going to put it? Well, obviously back on the stack. So we have this thing back on the stack, the result of A times B. And then we move further. So we do again, load fast of C and load global of D, which we need to compute the binary operation of asterisk multiplication of C times D. So we take 2 things from the stack, C and D. So now there's only one thing left on the stack, which is the result of A times B. That is still left on the stack, right? Because we take things from the stack from, from the uppermost element. So the element that we added, the C and D from the stack, calculates C times D and put the result back on the stack. So how many elements do we have on the stack right now? 2 of A times B and the result of C times D. But we still have to action happen. So we load fast the argument E, local, which is why we can do load, and do another binary operation. We don't do any other load because the other operand of our division is the result of C times D that was already on the stack. So this is how you can see the stack composes very well, because we are reusing what we've been doing, that it's already waiting for us on the stack to make this calculation. So now with the result of C times D on the stack and with E on the stack, we can calculate the division. We're doing this with binary operation 11 of division And finally, we have the result of this entire division. So how many things are on the stack left? 2. The result of A times B and the result of the division. So now we can finally say binary operation of plus. Now we're adding things together, taking both of the things from the stack. Now the stack is empty. And now we're doing plus, we're doing the addition. The result of this back on the stack. So finally, after all of this expression, there is one value on the stack, and this is returning from the function. So cool, like maybe this was bending right now, but what is to remember is that this is how Python worked day one, and this is how it works to this day today. The interpreter part means is that the bytecode used for this uses the stack machine to kind of take its values to make sure that it can act on things that are ready for it or data that is ready for it, but it doesn't really know what they are. So it's an interpreter that is very dynamic. This binary operation of multiple or of adding, of addition, can work on very many types. You might think, oh, if they're integers or maybe floats or something, but also be a string and a number where you're just gonna, multiply the string by this many, like, I don't know, a string of A times 5 would. So we will have very flexible operations in those bytes and sometimes be very easy and sometimes be very complicated to do. Add things, but adding things might also be adding strings. It might be adding user-based classes. You can actually implement those operations as well. So Python needs to know how to implementation for every such edge case is part of this super complicated binary op. So Python still works like this today. I already told you. If we want to look inside how that works, it's somewhat convoluted right now because of the improvements that we're making to it. So looking at a little bit of an older version of Python, you can literally see still the big interpreter loop that runs opcodes one by one. And that lives, used to live in ceval-c. This functionality is still in ceval-c, but it's a little more hard to find. So this particular loop actually selects what the next opcode executes it. And there were versions of Python where you really had a switch with opcodes that were implemented right there in this big loop. So based on what next should be executed, Python would select, for example, this load fast that you can see right here. And we talked about how load fast works. So here, like, obviously it's getting a local, it's doing some reference counting, whatnot. That is not very important right now. But the big point of you understand is that this is Python interpreter that, like, in the end, in your mind, you should understand as a loop that executes opcodes one by one. And this is very flexible. This allows us to do many fascinating things, but also is somewhat complicated when you use it. So we're going to be talking optimization next. But before we get to that, let's focus on the fact that doesn't matter how cool this interpreter stuff is and the stack-based machine, like, it's amazing how flexible this is being such a simple concept, but you're not here because you like stack-based virtual machines and stack-based interpreters. You're here because of some killer app. In my day, when I started with Python, I just wanted to have a website. Ideally, I could afford a web server back in the day and put my own sort of big system there and write my own website that maybe somebody else than just me and my dad would visit. It would be amazing. But I couldn't afford that, obviously. If I could, what I would be using is this killer app of Python in the late 90s, which was Zope. Zope was this because it was hyper dynamic. It was a system that allowed you to use Python at your website, but in fact, you wrote it inside the website. So for everything, HTML templates and all the files that you've been downloading, but also code for the website as part of the program, as part of data. So you'd be editing Python files, seeing the changes that you're making sort of dynamically happen on your website, like essentially at the same time, which today it's like, okay, first of all, maybe you don't want to operate your data with a website. That's not a great idea. So yeah, like those were times where those concepts were still being developed and it wasn't quite clear a good idea or not. But more importantly, this sort of sounds pretty modern, that like you're making changes to a website and you're seeing results of this right away. Was kind of world changing. One of the first systems that allowed this, and the Plone content management system built on top of that, was so popular that by the mid 2000s in the European Union, where I'm at right now, you really had to say why you don't want to use the Plone CMS if you are developing a website for a government or a public organization. It was simply the thing to do back in the day. But to run a ZOP, you had to have your own machine with a static IP, put somewhere a center would run so that people could connect to it. And it wasn't meant to be. In fact, most people would only use a shared server that somebody put on the internet and use PHP with that. And that's what I was doing, actually, right? So hence the image here, actually, because the most popular way to run PHP at the time was Apache. This system of processes where every request that came to the server would fork another sub-process, and that sub-process would actually just compute one request and shut down. Later on, there were updates to use threads for that. Came mod PHP that allowed very easy, cheap hosting, and I was worked. But Python wasn't really a great choice then. Like ZOP would require you to have an entire server for you. So people wanted to put Python inside Apache just as they did with PHP. Mod Python. And that was a possibility for Apache as well, but it turned out that. So in the Python process, when you are running your program and you have globals, and globals not only include your variables, but also your mod, like imports, right? And so on and so on. So those things are just global where the most common sort of optimization of the day, those would want to run for separate users. If you had a single web server actually working for little Łukasz and, I don't know, little Caroline and little Marlene and so on, what we want to do is all of their data should be separate. Otherwise, it's not only insecure because they could, most probably it would all just crash because you would want to start a library in some version where somebody else wants the same library in a different version, and that wouldn't shared data space. So what you wanted to do is to isolate them, and that was long before Docker. So what we did, by we I mean other people way older than me, because I was too little to really contribute to anything at the time. What Python did at the time was to create this concept of sub-interpreters, where you could start a new interpreter in your process, and that would have its own sort of data that is entirely separate from everything else. And that was working for mod Python pretty well. If you really tried, you could probably still run it today. I don't recommend it, but it is a possibility. So that was allowing us to run multiple independent applications inside the same process. Until very recently, they all still shared a global interpreter lock inside the process, meaning that only one Python instruction was able to be run inside this whole Apache server. That only changed in Python 3.12. So that was not really a great design. So let's talk about this, our gold ball and chain of Python, the global interpreter lock. So what Python needs to do is it needs to protect its own internal data structures from parallel modification. What I mean by this is, imagine you have a dictionary. So any dictionary that you have and you add it from multiple threads, if you are adding a key and in another thread you are deleting a key from the same, you could in which the internal state of that collection in Python becomes wrong. And in this case, that would cause the crash of the process. Or in a better case, if somebody writes to it and somebody else reads it, they would just see silly data. Like, for example, a key that exists, but its value is null, like the C null, the ugly null. Or if kind of counting how many keys are there in a dictionary, it would tell you a number that is not correct with the actual number of keys that are inside the dictionary. So all terrible things. So Python has this global lock that protects those things from just becoming out of sync. And more importantly, maybe, well, equally importantly, Python uses reference counting for memory management. So in a dictionary, the reference count of the dictionary is going to be increased, but if somebody else is doing the same thing, it's going to be increased, and so on and so on. But at the end, there's a very important moment where every user of it, every function call that exits is going to decrease the reference count by one, by one, by one, and at some point it's going to reach 0 so we can free the memory. If those increases and decreases of reference counts went out of sync, what that would cause is Python to either crash because it tried to access data that is no longer in memory, or it would cause memory leaks because things that you should have been freeing, you're not, because the reference count is invalid and it says 2, but it should be 0. If it's 2, but it should be, nobody will ever come to decrease it again. So it will be stuck until the process is dead, until the process is finished. So we have this global interpreter lock, and that lock allows us to make sure that all of those operations stay correct with the light of the multiple threads that are running inside our process. So that's correct. This causes things to be pretty effective and performant. You might be, but if you have to protect all those operations, between threads, it is better to just use one lock for this than to use a fine-grained lock for everything, because multiple locks are just kind of longer to acquire. There can be lock contention as well. And more importantly, if you have many locks, it can lead to a so-called deadlock situation where one thread holds lock A, another thread holds lock B, and now they're waiting on each other. Everybody is waiting on the other lock, so they will never be able to resume. So those situations are pretty tricky. So one lock was a really great design at the time, until, of course, you come to sub-interpreters, in which case, if you share this global lock between separate sub-interpreters, you're just wasting time, right? Because only one sub-interpreter can be running at a time. So why was it that the global interpreter lock had to be shared between the sub-interpreter? The reason why was that from day one, Python was constructed as a glue language. Guido was always saying that we have this language so that we can orchestrate low-level code in C and execute it in a way that is readable to humans. In fact, initially, Guido did not expect that Python applications would go anywhere above 500 or 1,000. Expected it to be really small scripts. And now we're running multiple million line of code bases in Python. So, clearly, the design held with this new sort of world where everything can happen. But from day one, Guido expected that the key to success for Python is going to be the ability to interact with C. And we call this the C API because it goes both ways. It not only allows you to call C, but it also allows C code to interact with Python back. So it can create Python objects, it can call Python functions, and so on and so on. So with this C API, we have not been historically very forward-thinking in terms of parallelism. You have to understand Python was developed in the late 80s, and that design held strong for a long while where you only ever had one processor per computer, maybe 2 cores, but that's at best for, until mid-2000s, that was the case. So the C API that third-party users did not have any isolation that would allow for multiple locks. So stabilizing this and making changes to the C API took a long while, took multiple years of effort. First with the stable ABI, so the binary interface, so that you could run your C extension with the future version of Python without recompiling it. The limited API that allows you to not have to rewrite your C extension every Python version that is released. And then we had binary wheels, which are the binary packages X PyPI. Before that, we had eggs, but egg format was insufficient for valid binary transfer for different platforms. They were somewhat tricky to analyze statically. So wheels, much better format. And later on, the Mani Linux sort of target platform that allows you to just compile a binary wheel for Linux. Obviously, there's many, right? And they have very many libraries on there on the system. So how does that work? Many Linux abstracts it away, puts it in a rather conservative package of dependencies, and when you're building your wheels against that, it is very likely that it's going to work on essentially all Linuxes and for sure on a subset of the distributions that we claim support for. So that's the C API being better and better over time. But sort of independently of that, Eric Snow has put in alert to make sub-interpreters really separate, including the global interpreter lock there. So he was able to make it such that the global interpreter locks are actually per interpreter locks right now, starting with Python 3.12 actually. So sub-interpreters isolated, and they have the opposite problem now where they cannot easily share data, sort of a challenge that is still ongoing with the sub-interpreter feature. And in 3.13, the amount of data that you can share between them is better. There are more data structures that you can use them between interpreters cleanly. So I invite you to just see what's new in Python 3.12 to look at that. Anthony Shaw, by the way, is doing a lot of work. Interpreters are viable already to use with web applications. But going back to the global interpreter lock, wouldn't it be great that anyway? Yes, and it has actually we were talking about, even in the types of ZOP, people would be like, wouldn't it be amazing to be able to Python things at the same time? So Greg Stein in 1999 proposed dropping the GIL for Python 1.6, but his implementation was too slow, so it was rejected. Larry Hastings did a gilectomy in 2015 for Python 3.5, and again, that ended up being not only too slow, but also to not scale with adding more threads. Because what you sort of expect is that the more threads you add, if you have physical cores to cover them, the faster your program is going to run. And in this case, we learned that this was not the case. Actually, what we had was the more threads you added, the slower it was going. So that was somewhat frustrating until Sam Gross, working at Meta, came in 2021 with a prototype of a remove show that not only move the global interpretable lock, but also with other related changes, make it scalable and not so much slower than a vanilla Python 3.9 interpreter. So this made a lot of kind of, I don't know, like they talk about the topic and was everybody was very interested, but there were obviously big challenges to actually make this happen. So in 2023, Sam wrote PEP 703, which I was sponsoring. I am a big supporter of this effort. And that was targeting, which was just released earlier this week. So this doesn't actually remove the GIL for everybody. If you're going to be downloading Python 3.13 today, you're going to notice that by default, it still has the global interpreter lock, works just for. So why is that? Well, this is a huge change. This change actually already kind of describes the process to moving to this new world, because the PEP is actually called making the global interpreter lock optional. It doesn't say that we will be making it, we'll be removing it right away. What it is saying instead is making it optional. Why? Because again, the C API that third-party developers are depending on will have to be adapted to this new world where there's actual parallel execution. So there is a level meaning your applications that previously would be working just fine because they were essentially serialized, now won't be serialized, now will be actually running in parallel. So there might be bugs lurking there that you need to fix. So for Python 13, what we're going to be doing is we're going to be making it possible for you to build your own Python 3.13 and run it with your applications, with your libraries, and with your frameworks, and see whether this makes things better. Adopt some changes, whether this actually scales, whether you are seeing the positive of the change, or maybe it's crashing, you cannot find the bugs, it is actually slow, and so on and so on. So the community now needs to really react to whether they want the GIL gone or not. So I wouldn't say Python 3 makes the GIL optional for end users, because all the frameworks and libraries have to be ready for that. I would more say that the GIL is now optional so that the authors and the maintainers of frameworks can make them ready, so that the next version of Python is going to be the moment where we're going to ask everybody to test the free-threaded version of Python. We call the version of the GIL free-threaded because it allows every thread to run free, so with full parallelism. Sam had to make many changes to Python to allow for those things to be not much slower than before with single-threaded performance. And he made changes like biased ref counts, memalloc, a new allocator for Python, and thread safety for many places of Python, like the collections that we have, even the threading module situations where assumed that it is running on Python that has the global interpreter lock. So now a lot of those things had to change. But all of this, if you just put locks low, so a part of making it usable was lock avoidance with algorithms that are sort of bleeding edge, that in the most popular cases, which is pretty. So that's the goal in Python 3.13. If you download the Windows installer, actually there is enable this experimental. You can actually run this, experimental interpreter. Other than that, I wouldn't necessarily yet, but if you're maintaining a library or a framework, yeah, this is the time for you to actually check whether this gives you any wins already. Let's move to the just-in-time compiler, because the interpreter is getting way more sophisticated right now. The opcodes I showed you look somewhat different now for performance. Remember that the interpreter loop with the giant switch statement, so like this one right here, like that is gone now. There is PEP 659, spearheaded by the Faster Python team at Microsoft, made Python what it means is if you have a for loop, and in that for loop you are adding two numbers together all the time, right? Like every iteration, Python will at some point, those are only numbers all the time, specialize from binary op, which I told you is an extremely generic operation. It can add together two strings, it can add together two user classes, and it can add together numbers. That last operation should be the fastest because you can really do this very quickly on a computer. So now the specialized interpreter in Python 3.11 actually already find the situation where you're only adding numbers together and replace the binary opcode into a specialized add of just integers. And this is going to be quicker. The same goes true for the for loop itself, which if you're using it with a range, is a very popular version of a for loop, the specialized interpreter will notice it and replace for iter, an opcode, to for iter range. 3.12, the interpreter is actually now generated itself from a domain-specific language, so things like recounting and error handling are automated, which removed an entire class of errors that we had before because everything was manually written, and manually is not really that great. So now we are gathering runtime profiling data for user code, and this leads to the just-in-time compiler. You can now have something that will change all of those opcodes into optimized machine code specific for your processor. The entire loop of opcodes altogether. We're not in that loop anymore. We're executing a custom machine code that is optimized to run up. Quick JIT that we want to see is already kind of being developed for Python, and there is statement already 13. So the way it is implemented is, again, amazing that we can have this, but it is one of those things that are going to be changing in time, that we're going to develop over time. Currently, we are basing our JIT on a paper about Lua, how you can automatically generate a JIT from sort of pre-computed, pre-compiled pieces of code made by LLVM, made by a C compiler, and then you copy and patch them together, just like Mad Libs. So you can copy those pre-computed pieces of code, enter data where it's supposed to go, patch those things together into a longer story, like the sentences here, and boom, this is now going to be super fast. This should be only 35% slower than a handwritten JIT, but allows us to actually target all platforms faster, and it should also make more optimizations possible later. And most importantly, it only makes the LLVM bit a compile time dependency for Python when you're building the interpreter. You don't have to have any of that to run Python, which means still platforms can be targeted. But the point of this talk is really that a lot of changes are incremental from 0 JIT to all JIT in one release. So currently, the JIT that you have here in Python, it is not really faster yet. The reason why is that this entire machinery of copy and patch, this entire recognize when to JIT and so on, setting this up is a lot of very tricky work. And Brant Booker's works, it is 0 times slower, or really 0 times faster now. But in Python 3 to 14, soon you're going to see some positive changes in terms of performance with this, because the focus now is moving from setting it up to faster. So we also detect and optimize and execute hot paths using a new kind of interpreter now called Tier 2 that uses micro operations that are atomic, easily typed. Those can reorder operations. So you can, for example, consolidate a null check, a non-check to the start of the trace instead of repeating it multiple times, which makes things faster and so on. I guess in the future, you can expect the JIT to be a crucial version of a crucial functionality of Python. But for today, this is still sort of, you have to build your own Python to see this. So ideally, I would want us like to just consider this as a marathon. We're not releasing where like every year you can expect revolution, but there's gonna be a revolution. Only it takes time. Yeah, so here on the image you have a global hawk surveillance drone, which is also tier 2, meaning it can. The longest flight was. I just thought tier 2. You know, it's. Okay, so you have to know that all of this is only possible because there's a lot of investment in Python now. So we have core sprints. I just returned from Bellevue, Washington, where an annual core sprint was held this year at Meta, which thanks to their efforts, like we can actually see a lot of this positive change happen. And people at corporations like Microsoft, Bloomberg, Red Hat, and until recently Google, like are making Python because they're hired to do so. But most importantly, we have our Python sort of foundation, which allows us to like keep Python healthy without being overtaken by a single corporation. For hiring me, and thanks to Meta for sponsoring my position actually, and providing the tech to generate the images I used. If all of those things, all of those technical things sound interesting to you, I'm running Salgado, the and a steering council member, so you can actually subscribe and listen to things that we cover with how Python is changing every 2 weeks. And in fact, the latest episode is on how the core sprint went, and on that event. My name is Łukasz Langa. I'm very happy to be here. Thanks for having me. I'm not sure we have time for questions, but if so, I'm happy to answer them.
All right. Let's make it louder, louder, louder. Thank you very much. Thank you very much. Insightful session. I'm not exactly a developer. I'm actually a novice, like a negative novice developer. But one thing I've learned from the session is that we have a stack, right? And on this stack, we have some elements on the stack. I don't know why we have the stack, but all I know is that it's on the stack, and we put off the elements sometimes and then puts them back. Sometimes they are A multiplied by B, other times they are B, and then after multiplying them, we put them back, do some binary operations there with additions and multiplications, you know, and then back on the stack. So guys, get stacks, right? Thank you, Lucas. Thank you, Lucas, for the session. But I want to have one person or maybe two ask very, very brief questions and then very straight to the point, friend. Ask your question if you have one, and then we prepare for the next sessions.
All right.
Anyone with a question? No, you have to come here because we want to see you. So who is asking quickly? Don't be shy, don't be shy. Yeah.
So, good morning, everyone. And I don't know what time it is in I think it's morning. Yeah, but I just had I had a lot of questions that I was saying that I should ask on. One and briefly. Okay, so my question is, there are all these changes coming into Python, and I'm worried it's a bit complicated because one of the selling points that people got into Python before was because it was easy to use, easy to learn, and easy to do things with. But now with all the machinery and changes coming into Python, I think it's becoming quite hard. I've been reading a lot of typing PEPs, and a lot of typing is coming in to make it the code to read. So all this are they making Python to use or harder to use? That is my question.
Right. Great question, actually. So the way we are Python development right now realizes one thing, that the killer application of Python in the late 90s, who knows about Zope now, but it was where most of development of Python was focused on then. Even like Guido worked for the corporation that developed Zope for a while. The killer application changes over time. These days, obviously, it's data science, it's AI, right? The ability to actually not only on CPUs, but actually maybe now mostly on GPUs. So the world is changing very quickly. We, as the core developers of Python, realize that there is no one group of Python users. There is very many use cases. So data science, very important for us. People who are still running web servers and doing pretty cool things with them, like fast. People who are running it client side in the browser now, important for us. Embedding it in mobile applications for iOS and Android, important for us, which is actually a new feature in Python 3.13 right now. So all of those things have to sort of live together under one roof. And now development of Python will kind of make it more challenging for you to understand what is going on if you want to understand all of it, every part of it, and be the Python, all the possible features, all the possible features. Position is that it is perfectly fine for you to be a Python user annotations, which is why they are optional. It is perfectly fine for you to run any async IO code. So you're not interested in async and await. And it should be perfectly fine for you to use Python and not understand free threading and so on. You should be high level are going to be developed right now before Python 3.14 goes out, such that like, oh no, what's by multiple threads at the same time, and so on and so on. So Python becoming a larger language. Like, that is true. This is a real concern. However, like, learn about all the pieces on day one to be productive. In fact, still, kids these days are learning like programming with Python in grade school, and they just start with a small, tiny subset, maybe with a turtle module or something, and they're pretty happy to accomplish with a really small subset of the language. So hopefully this is actually working out for us, and like, you can agree that you can be pretty productive with just a small part of Python. If not, you should be raising those concerns to us while a new version of Python is developed. So if you actually follow what is going on in our forum, which is discuss.python.org, especially on the core development category and in the PEPs category, you can have feedback about how, because it's going to make it harder to teach Python, or you just want to understand how it's going to compose with some other feature, and so on and so on. So you, as a user of Python, also have influence over. We're going to reach a future where nobody says that this is too confusing of a language to use.
Okay. Thank you very much. I yes, I would have liked.
Thank you. I was very happy to be here.
Yeah. But
Yeah, getting ready for the next session that we have on our agenda right here in the Pacific.